Hello, we're Group 3, and we're going to be demonstrating our multi-sensor passive ranger. My name is Pedro Abres from the College of Optics and Photonics.
I am John Haynes from the College of Electrical Engineering.
My name is Alina Sankara from the College of Optics.
My name is Taylor from Computer Engineering.
For our final demonstration, we're going to be having a car going towards the camera as shown here in this diagram. We're going to be setting up cones, which you can see here in the picture on the right, and we're going to be measuring distances with a distance measuring wheel, and the total available distance we can travel is 107 meters. In this demonstration, we're going to be looking for these specifications and requirements. We would like to achieve a range estimation accuracy of 10% of true value, a range estimation speed of 1 time per second, and an object motion tracking within 1 second. So here are the results of the calibration. On the left, we have an image of a very barely distorted image. Here we have the detected points and the reprojected points, along with the mean error pixels to detect outliers, and also the extrinsic parameters of every checkerboard pattern. We used many to ensure we had the most accurate calibration. Here we show a distorted image on the left and an undistorted image on the right. We have calculated the parameters for radial distortion, tangential distortion, as well as the image matrix. After running this, you can see how well the undistortion code works. This is actually able to run live on the system itself.
This visualization is able to show extrinsic parameters and map out the cameras in relation to the checkerboards. This slide shows the results of our calibration with a camera-centric view of our extrinsic parameters. It also shows reprojection errors and labels outliers.
Now we're going to demonstrate the time that it takes for the single shot detector algorithm to pick out an object from the scene and proceed to display it. As we can see right now, the program is initializing. The single shot detector network is loading, and instantly, as soon as the frame appears on the screen, we can see that we draw a bounding box around the target, as well as output the range and the X and Y coordinates in the frame. Now we will demonstrate the single shot tracking algorithm, tracking both a truck and a car. Both of these types are defined within the MobileNet single shot detector that we implemented using TensorRT. It may take a little bit of time for this tracking algorithm to pick up the truck and the car, as you'll see, because there simply just aren't enough pixels for the algorithm to match the object with the class through running it through the neural network until more of the object is visible as it approaches the camera. Once we've successfully picked out the location of the objects in both of the stereo camera feeds, we will then pass them over to the stereo module of our codebase. In the stereo module, we take the positions as coordinates and average them out, which will give us a centralized position that we then use as a point of reference in the rectified image. At which point we then proceed to perform the disparity mapping algorithm to extract the position and range of the object. We found that this particular approach tends to get better as the object becomes closer to the camera, as there's a greater disparity between the two images at this point. We expected this when we were designing our project. As we can see, initially the truck does not get picked up by the algorithm. However, we'll see that as the truck comes closer to the camera, it'll begin to be tracked. On each frame, the algorithm will continue to draw a box around the truck as long as it passes a 0.5 confidence threshold. We could lower this threshold to possibly improve the detection at farther ranges by detecting objects that is less confident about. However, we feel that this will also cause our detection to become significantly noisier and pick up redundant objects. Here we're demonstrating the SSD algorithm to track the object, as well as the stereo disparity mapping method to determine the range of the car. As we can see, initially the car does not get detected by the stereo algorithm. However, as it does approach the cameras there becomes enough detail for the algorithm to correctly draw the bounding box and extract the coordinates of the car. Next, we will demonstrate the stereo system tracking and ranging a person in the scene. As we can see, the system does a good job of picking up the person on each frame, getting their coordinates, and computing the z-axis or range value. Occasionally with the stereo system, we notice that we would compute a range of 0. We believe that this is due to the fact that the SSD algorithm needs to detect the person for both sides of the stereo system, that is the left camera and the right camera. If one of these sides does not detect the person, then our math will fail and will result in a 0z value. Given more time, we would be able to find a solution to rectify this problem.
This set of images depicts our stereo system detecting a person and ranging him at different distances. It's able to detect and range him well within about 10 meters, and it's also more ideal when the lighting is able to outline him more clearly.
Here we have the IR ranging using the contour object detection. When it was first detected, it gave us a range of about 46. Then, as the car moves closer to the camera, the surface area detected is going to be larger, and we're going to get more pixels. And this calculates to closer and closer distances to the IR camera. Additionally, it can be seen that the car is actually going in zigzags. Even though this is happening, it is actually able to keep up with the range quite well, whereas sometimes it gives us an error when the car is completely sideways and the motor area seems to be a lot bigger. These are the kind of things that affect the ranging in the system. This is the housing that we ended up with at the end. On the left side, we have the open rooftop view with the cameras in the microprocessor. In the middle, we have the closed system with the roof on and some breathing holes. And on the right, we have the connections for USBs, HDMIs, and Ethernet to work remotely.
This is the first design, which is relatively efficient at 87% at max load. The problem is that when the input gets connected to the power outlet, this trips the circuit breaker. This happens because the rushing current is too high. To solve this, I need a 1-to-1 transformer with a capacitor on the input, which would reduce the capacitance seen by the wall outlet down to usable levels. This is the secondary design I came up with. This outputs 12 volts for one voltage regulator and 5 volts for the other regulator. This includes a 120 volt to 12 volt AC to AC transformer, which goes into a rectifier and outputs to a linear regulator. I couldn't get this to work because I couldn't test with enough variance in load to keep the voltage regulator from overheating and provide the required load and voltage level from the Jetson Nano.
Future work and improvement. So there's several areas that we could definitely improve our project. First off, the power system integration. Given more time, we could fully integrate our power system. More processing power. The Jetson Nano is simply a microprocessor. Were we able to scale up to a full-size computer or cloud computing solution, we could process these images at a far higher rate and more quickly extract real-time range data. High resolution cameras. If we had more pixels, we would be able to extract objects because we have more pixels of detail. Finally, training our own neural network using IR images would definitely improve our detection rate on the IR camera. Thank you for your time, and I appreciate you all for coming to our senior design presentation. If you have any questions, feel free to ask us anything you'd like. We will do our best to respond to the best of our ability.